advance for anything doofy that might accidentally come out of my mouth because it's been one of those days. We're going to finish hopefully chapter 14 on Friday. Chapter 14, actually, hopefully we'll finish it on Wednesday. The assignments will be due on the 3rd, which is Monday. I do believe that I thought I had written down that the test was to be due by 11:59 p.m. on the 3rd, but realized that the final will be due by 11:59 p.m. on, I think I had initially said the 5th, but thinking about it, because their test is just the day before, we'll push that back to the 6th. Next week, Wednesday and Friday, attendance will be optional. It'll be to just go over things you have questions on. On Friday of this week and Monday of this week, hopefully we'll have those 2 days that we normally take to tie up loose ends at the end of a chapter. Before we pick up from where we left off, does anybody want to look at anything from the textbook?
You go over question 3 on the first part of the chapter.
Okay, so question 3. Says a red and green die are rolled with the outcome, the pair of numbers shown on the 2 dice. For example, 3-1 is the outcome, where the red would be 3 and the green would be 1. Draw a diagram showing the sample space where each outcome is an ordered pair, showing the numbers of spots. Draw loops in the sample space diagram that show each of these events, and then ask which are mutually exclusive. Again, that idea of mutually exclusive, meaning that they have no overlap, they have nothing in common. I'm going to go real quick, and I'm going to copy this question and put it in a blank page at the end of the notes. And so this is from page 729, question number 3. Now that the picture for 2 dice we've drawn already, and we've used it a couple of times. Remember when we went through and we drew this picture for 2 dice? So I'm going to try to go through and snag that diagram. And add it to this page. And so they had said that the first one is the red and the second one is the green. And so here, when we filled in this table, the first numbers came from the top. So we'll say that those are a red die, and the second ones are on the side here. So we'll say that this is our green dot. Do you remember creating this sample space with the ordered pairs for rolling 2 dice?
Yes.
And so A asks us to circle where the total of the 5 is on the 2 dice. And so let's go ahead and let's circle that the total of 5. Actually, we've got that underlined. Nope, we've got the total of 6 underlined. The total of 5 would be here. So this is A. B asks for a total of 9 or more. So let's see, for a total of 9, I'm going to circle these, I guess, in green. 9 would be 3 and 6. 9 would be, I just replaced the battery, 3, 6, 4, 5, 5, 4, 6, 3. And any of ones below that would be more. So this would be B. And then C asks me to show where the green die shows a 5. And so I'm going to use, I guess, the red. The green die showing a 5 would be here. So this would be C. Everybody all right so far?
Kind of.
Okay. In A, we're just circling the pairs that add to 5, 1 and 4, 3 and 2, 2 and 3, 3 and 2, 4 and 1. In B, we want where the sum is 9 or more. So let's see, 3, this is 9, 9, 9, 9, and then the ones below it would be 10, 11, and 12. All the ones above it would add up to 8 or smaller. And C asks us to show the ones with the second die is 5. So those are all the ones where that second number is 5. A little bit better?
Yes, thank you.
Okay, and so now, which are mutually exclusive? Well, A has nothing in common with B. A has nothing in common with C. They're mutually exclusive. However, do you see how B and C they overlap? And so B and C are not mutually exclusive. They share some of their results. Better?
Yes.
Okay, great. Did anybody want to look at any others?
Yes.
Go ahead.
Have to look really quick on which one.
If it's going to take you a while to find it,
15.
on the same page.
Yeah, 729.
Okay, 15 says a standard set of balls is used to play pocket billiards containing 16 balls. So what they're talking about are pool balls. The balls are numbered 1 through 7 are colored. They're called the solids. 9 through 15 are colored by a broad stripe, so they're called the stripes. There's also a black ball that's not solid or striped, and the white ball that has no number on it. Draw a Venn diagram. You're going to have a loop for E, even numbers, a loop for F, the striped numbers, a loop for G, the solids. So then you're going to place in all of the, so for example, 1 would be solid but not even. 2 would be solid and even. 3 would be solid and not even, as opposed to 9 would be striped but not even. 10 would be striped. And so you're going to just place all of the numbers, all of the balls in the right loops of that Venn diagram. Does that help?
I'm still confused.
Okay. And I think I just accidentally closed that page. This is what happens when I actually accidentally press the wrong. So I don't want to do that. Wasn't one of these. So we're going to draw here a Venn diagram. And it says that E are the evens. F are the stripes. And G are the solids. So let's see. I don't think there should be any overlap here. I don't think any of the solids are also stripes, but there's our 3-loop Venn diagram. So 1 through 7 are solids. So let's see. 1 is a solid, it's not even. 2 is a solid and even. 3 is a solid, not even. 4 is a solid that's even. 5 is a solid, not even. 6 is a solid that is even. 7 is a solid that's not even. So far, so good.
Yes.
Same way, 9 through 15 are stripes. So 9 is a stripe that's not even. And so now, do you have a better idea of filling in the rest of the Venn diagram?
Yeah.
And then once you do that, you'll be able to count how many are in each category and use that to figure out the probability.
Okay.
Better?
Yeah. Thank you.
You're welcome. Okay, so let's look back where we left off. And I remember being in the middle of a sentence and my eye got distracted and I saw the time and realized, oh dear, we had run over in the middle of a sentence. We were talking about the counting principle. And what the counting principle says, that is, if one event can occur in M ways and another in N ways, they both can occur in M times N ways. Or we multiply. And so we already looked at that today, even that list of outcomes for rolling 2 dice. But if I look at the first die, it has 6 outcomes. If I look at the second die, it has 6 outcomes. And so when I take 6 times 6, that's where we get that there's 36 outcomes for 2 dice. So the counting principle says when we're counting how many ways something can occur, if it's a compound event, we found the number of ways each part can occur and multiply. Is everybody all right with that idea?
Mm-hmm.
So we talked about or in probability, it's kind of the same way. Or in countings, the number of ways A or B can occur is equal to the number of ways A can occur plus the number of ways B can occur minus the number of ways that they both occur at the same time. And with these, when we've got that N in front, we're asking for the number of ways, how many ways. And so our answers will be counting numbers. previously, when we looked at some of these, we were asking what's the probability? And our answers were fractions. So here, if I roll 2 dice, what's the number of ways I can roll a 2 or a 12? Well, the number of ways I can get a 2, there's only one. That's a 1 and a 1. The number of ways that I can get a 12, well, there's only one, a 6 and a 6. And they don't both happen at the same time. There's no way that the 2 dice can simultaneously add up to both 2 and 12. So here, the number of ways, I am sorry, this stylus is just, and I just replaced the battery over the weekend. I have no idea why it's not liking me today. I don't want to have to go out and buy more of those fancy pants batteries, but let's see, maybe I can get it to work. So the number of ways I can get a 2 or 12 would be the number of ways I can get a 2 plus the number of ways I can get a 12. And over here, these are actually mutually exclusive. So they don't happen at the same time. So I don't really have to subtract anything. So that gives me 2. Instead, the number of ways I can get an even sum, I think we looked at that previously and we had said that they were half even, but let's go double check. Let's see, evens, I have scribbled all over this picture. Should I try to upload it again? That one's scribbled all over also. Do we have a blank 2 dice? I guess that's the closest we have. So here I'm going to circle the evens in red. So the sum of 2 odds numbers is even, the sum of 2 even numbers is even. And as I circle the even sums in red, does everybody see that it would be half of the 36 outcomes, so that the evens is 18. I'm going to go ahead and in blue, circle the ones that are greater than 10. So bigger than 10 would be 11 or 12. And so greater than 10 is 3. But you guys notice that there's one sum that's counted in both. And so that sum that's counted in both, well, there's one of them. So putting these pieces together, even over 10 would be 18 plus 3. But then we'd have to subtract that one that's in both of them. And that gives me a total of 20. And so rule of thumb with probability, also with counting, is if you see that word or, you add the number of ways each separate event can occur, but you have to remember to look out, hey, wait a minute, is there anything I'm counting twice? And because we don't want anything to count twice, we have to subtract the number of things that are included in both. Does this example circling those numbers help you see that idea of when there's overlap that we have to be careful?
Yes.
So. Let's
Can you
go.
just stay on this page for one more minute?
One more question to do on this page, but if you need for me to shut up for a minute, let me
I
know.
just had to copy the chart down, so I'm just recircling the stuff and writing it down.
Okay. Again, everything that I write here, I put in Blackboard. If you want to just pay attention and get the writing down later, you can do that, or we can wait. Let me know when you're ready.
Okay.
So last one down here, deck of cards, you're gonna pick one. We wanna get a jack or a black. Well, how many jacks are there in my deck of cards? Is everybody familiar with the deck to know that there are 4 jacks? Or how many black cards are there? Half the deck. Half of 52 is 26. The or tells me to add it. But then we have to remember, are there any cards that do both? Well, sure, there are black jacks. And is everybody all right? There are 2 black jacks, 2 cards that would count as jacks, that would also have counted as black cards. And so that gives me 30 minus 2 or 28. I think cards are great. For these. If that's all right, then let's go to that next page. This is the word or in counting. And or means add, subtract the overlap. Next, we're going to look at the word and in counting, and that's where our counting principle said to multiply. And so if I toss 3 coins, how many possible outcomes are there? Well, for the first coin, there's 2. For the second coin, there's 2. For the third coin, there's 2. So the total number of outcomes would be 2 times 2 times 2, or 8. And I do believe we already drew this possibility tree, because if I'm counting, I only want the possibilities for 2 coins. And we said first coin would be the first set of branches, heads or tails. Second coin would be off of each of those, and it doesn't matter what came first. Either of the second coins can be a head or a tail.
Miss
Sure.
Triella,
Yeah,
how'd you get the 8? Did you do 2 times 2, get the 4, and then multiply it by the 2?
yes, ma'am. 2 times 2 times 2 is 8. That counting principle tells us to and means to multiply.
Okay. I'm confused. Okay.
Better now?
Well, I just looked at it as like 2 times 3.
No, it's 2 for each.
Okay.
First coin has 2 outcomes, second coin has 2 outcomes, third coin has 2 outcomes.
Okay.
Okay, it's coin 1 and coin 2 and coin 3. And as we look at this finished tree diagram, it shows us those 8 outcomes. This would be all heads, 2 heads and a tail, and so on. Things are a little bit different though, if I see this word without replacement. Without replacement, all of a sudden we're kind of getting back to that idea that we're putting a condition on it. And we talked a little bit about conditional probability. So this time, let's look at a possibility tree. This time we're not flipping the coins, but we're just putting our hands in our pocket and pulling a coin out. When I pull that first coin out, is everybody all right? It could be a dime, or it could be a nickel, or it could be a penny. With me so far?
Yes.
If my first coin is a dime, the dime's gone. Don't I just have for the second coin either a nickel or a penny? As opposed to here, if the first coin is a nickel, the nickel's gone. The second coin can only be a dime or a penny. And if the first coin was a penny, the penny's gone. All I have left to pick from is the dime and the nickel. And so here, do you see that this time there are 6 outcomes? For the first coin, I had 3 possibilities. But for the second coin, I only have 2 possibilities because one of them is gone. What's the possible value? Well, let's see. A dime and a nickel would be 15 cents. A dime and a penny would be 11 cents. A nickel and a dime would be 15 cents. A nickel and a penny could be 6 cents. A penny and a dime could be 11 cents. And a penny and a nickel could be 6 cents. So the possible values are 15 cents, 11 cents, and 6 cents. But we're adding to that idea of the first coin and the second coin, multiplying. That word "and" tells me to multiply. So the number of ways that A and B can occur is equal to the number of ways A can occur and then I'm going to multiply by over here, that's the number of ways B can occur, given that A already happened. And so this is putting that condition on. We're changing our sample space. So let's say we have a dozen donuts. Let's say there are 4 cake donuts and 8 filled donuts. And we want to know the number of ways we can get 2 filled donuts. Well, how many filled donuts are there?
8.
8. So we picked out 1 filled donut. Yum, 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 yum. Is anybody else a big fan of Paula's donuts?
Yes.
So I just ate, okay, it's one of those peanut covered cream filled Paula's donuts. I think those are the bomb. Yum, it's all gone though. Do I still have 8 filled donuts left to pick from?
No.
No, I ate 1. And so that second number is a 7. And there are 56 ways. And again, this went down because we ate 1 already. That condition, the first one's gone. So there's only 7 left. So then how about if I want 1 cake donut? Well, there are 4 cake donuts, and I'm going to multiply 1 filled donut. And is everybody all right here? Because the first donut that I ate was cake, I still have 8 filled donuts left. And so there are 32. And so this time, the first one being a cake didn't affect the number of fills. But we always have to keep that into consideration when we're counting. And again, I think cards gives me a good an example of when I have to take that into consideration. I have a deck of cards. I'm going to pick two. How many ways can I get both queens if I replace the first one? Well, for the first one, there are 4 queens, but I put it back. So there's still 4 left. And there's 16 ways of doing that. As opposed to if I didn't replace the first. Well, if I didn't replace the first, for the first queen, there's 4, but I didn't put it back. So now there's only 3 left. And that gives me 12. And that idea of whether I replaced it or not, when I replaced it, it didn't change the probability of the second, but when I did not replace it, it did. Is everybody all right with the difference between those two?
Yes.
Great. Then next example is along that same idea. Next example says, how many different 3-digit codes can I form if I can repeat the digits? Before we go any further, think back to Math 108 when we were looking at our number system. Does everybody remember our number system is base 10? And that's because we have 10 digits. We've got 0 and then 1 through 9. And so over here, I have 10 digits. I want to pick 3 digits. For the first one, I have 10 choices. If I can repeat, for the second one, I also have 10 choices. And the third one, I also have 10 choices. And so 10 times 10 times 10 would give me 1,000 different numbers. The second part of the question says I cannot repeat. So after I used up one of the numbers, I can't put it back in the mix. And so here for the first digit, I have 10 choices. For the second digit, I have 9 choices. And for the third digit, I would have 8 choices. And this would multiply into 720. And is everybody all right with the difference between those two?
Yes.
And so that gets us into certain things that we're going to talk about. First is permutations. Permutations are agents of objects. Over here, what we have to remember is that the objects cannot repeat. With a permutation, the objects are different. I'm going to say they're distinct, which means they're each different. And with permutation, again, like I have in caps up there, order matters. And so if I have P, N, R, N is the total number I have to pick from. And R is the number that I'm choosing. But what's important to remember is in a permutation, order matters. And so over here, when I could not repeat, that would be like permutation. There were 10 digits. and I picked 3. And I have to apologize. This is the notation that the authors of your textbook use. If you've seen this previously in another class, that's usually written 10P3. There are different ways of writing the same thing. And so we had 3 things we wanted to pick. For the first one, we had 10 because we cannot repeat. We have 9, then 8, and that gives me the 720. And again, we have to remember that if it's a permutation, order matters. You also hear about a combination. Combinations are selections of objects, and so the objects here also cannot repeat. The objects have to be different, so they're distinct. And with these, order does not matter. For combinations, we'll use C. The first number is how many we have to pick from. And the second number tells us how many we're choosing. And so here, let's say there are 4 students sitting in a row, A, B, C, and D. They have these really creative names. I want to pick 2 to do 2 different problems. Let's say one problem is really easy and one problem is really hard. Because the problems are different, would it make a difference to you if you got the easy one or the hard one if you were going to the board? I think so. So since they're different, their order matters. How many ways can I select them? Well, with what we've been alluding to, we have 4 students to pick from for the first, 3 from the second. So I'm guessing there will be 12. To make that ordered list, A could do the first, B the second, A could do the first, C the second, A could do the first, D the second. Or B could do the first, A the second, B could do the second, C the second, B could do the first, C the second, B could do the first, D the second. Or C could do the first, then A, C could do the first, then B, C could do the first, then D. Or D could do the first, then A, D could do the first, then B, D could do the first, then C. And order matters. It makes a difference to us who did the first problem, who did the second problem. So that's the permutation. Instead, if they're working together, well, if I work with you, that's no different than you working with me. So if they're working together, order does not matter. So if A works with B, then B with A is not a separate choice. If A works with C, then C with A is not a separate choice. If A works with D, then D with A is not a separate choice. If B works with C, then C with B is not a separate choice. If B works with D, D with B, B is not a separate choice. Then I could have, we've already got C working with A and C working with B. We could have C work with D. And we've already got D paired with everybody else. So this time there are only 6 ways. And from this example, does everybody see there's 6 ways for the combinations? If order does not matter, it's a smaller number. So remember that if I have this, I'm picking the same number from the same group, combinations should be smaller than permutations. So let's go through and let's look at formulas that can be used to help us figure these out. Is everybody all right if I turn the page?
Yes.
So in order to look at these, I have to look at something called a factorial. Has anybody heard of a factorial before?
No.
It's the product of a natural number and all the natural numbers less than it. Factorials are shown with exclamation points. And so n factorial means I'm going to take that first number n, then I'll multiply it by the number 1 less than that, and then the number 1 less than that, and I'll keep multiplying until I get down to 1. So for example, if I have 3 factorial would be 3 times the next number 2 times the next number 1, or 6. Instead, if I have 5 factorial, then I'd start with 5 and I multiply by every number less than 5. So let's see, 5 times 4 is 20, times 3 is 60, times 2 is 120. This definition is only for natural numbers. 0 is not a natural number, so we have to define 0 factorial separately. I'm going to rewrite it so I have a little bit more space. 0 factorial will always equal 1. And so permutations, there's 2 ways of looking at it. One is this formula. And the other is to say, okay, I'm going to multiply starting with n until I have r factors. I kind of like that second one better, that second definition. But let's look at it. I think when we looked at 10 digits, pick 3. No repeats. That would be a permutation from 10. We're picking 3. So since we're picking 3, we need 3 spaces. And then it would be 10 times 9 times 8. And that's where we got that 720. Instead, where we had the 4 students, we wanted to pick 2 for 2 different problems. Well, that would be permutation. There were 4. We were picking 2. Since we're picking 2, it means I have 2 slots to fill in. For the first one, I have 4 choices. For the second one, I have 3. And so we had those 12 different arrangements. Instead, if I wanted, let's say, a permutation of 5, pick 5. Well, 1, 2, 3, 4, 5, starting with 5, multiplying would give me my 5 factorial.
Good question.
Fair enough.
Okay, so for the first part, you said pick 10 digits, the 10 digits, and then you said you put the P and then 10 and 3 in parentheses. So we have to pick from the 1 through 10, right?
Yeah.
Okay.
No, 0 through 9. We were picking.
Okay. So I
Okay?
thought you said natural numbers because I didn't know 0. I forgot 0 contains a natural number.
Yeah,
it's just whole
0
numbers.
is not a natural number, but it's a digit.
Okay.
Okay. Now, instead, we had said combinations is a smaller amount. And the way combinations becomes a smaller amount is we take our permutation and divide by that second number factorial. So where we had 4 students, we wanted to pick 2 to work together. Here, order does not matter. And so that's a combination from 4, we're choosing 2. And in order to find that combination, we're going to do like the permutation, 2 slots, starting with 4. But then in the bottom, we're going to put our 2 factorial, which is 2 times 1. And so that gives us 12 over 2, or our 6. So let's have you try one. Let's say combinations. Let's say I want combination 5, choose 3. The denominator is at 3 factorial. The numerator is 5 permutation 3, or I'm going to start with 5. And you should have the same number of factors top and bottom. And so if I were to just multiply, that would give me 60 over 6, or 10. Or if you want to reduce that fraction before you multiply, you can. And looking at my clock, it's that time, which I had thought we might go a little bit further, but we just have one more situation to look at next class. And that next class, if you look, most of the rest of the notes are examples. On the 3 pages down, there's a block with properties of probability in it. We'll go through that. And then those problems after that, we're not going to look at odds or expected value because of time. I don't think that you have homework on odds and expected value. If you do, I will let you know next class, that you can skip those problems. But is everybody all right with what we talked about today?